So good afternoon and thanks for coming. So I'm going to present the SuperStack superoptimizer. And this is a work by researchers both from Complutense University of Madrid and Monash University. So the main premise of this work is that efficiently managing an operational stack in a stack-based language is challenging. And as an example, we are going to consider the following sequence. This is a sequence of a WebAssembly program in which, well, it is quite simple. We are going to analyze it. So first, we are invoking the function random, and we are storing the result in the local variable L4. Then we are computing a store operation. We are storing another value in the corresponding register P0. And finally, we are just storing another constant in the corresponding variable. So while this code might seem optimized, there is still a lot of room for improvement. So we are now going to consider the following code. Okay? So the problem with the previous code is that it didn't take advantage of the operational stack. So let's analyze this here. First, we introduce the constant 0 in the stack. Then we introduce the constant 1 in the stack, and we apply this the operation, which is an operation in WebAssembly that both stores the corresponding value in the stack and in the register. So we just have one store there. In the next step, we compute, again, this expression and store it. And finally, thanks to the values we have previously introduced in the stack, we are going to just apply the store operation. So how have we managed to remove 3 instructions? So the first thing is that in the original code, we invoked the function random and stored the value in a register. But now we are invoking it directly, so we don't have to retrieve it. Also, thanks to this, we access register L4 just once when we are applying the T instruction, whereas in the original code, we're accessing in 3 different points. The same happens with constant 1. As we are using a T instruction, we just apply it once, while in the original code, we applied it twice. And finally, well, we can do the store operation, but we have introduced the stack elements in several instructions before. And this is the kind of optimization that we want to achieve with our approach. I just want to emphasize something else, and this is that we have to keep the order in which the invocation of the random function and the store operations are applied. And this is because the random function could modify the memory, and this would affect the overall code. So the limitation here is that this type of optimizations are very difficult to achieve through pre-cooked transformations. And our proposal is to apply superoptimization techniques. So superoptimization is a technique that aims to find the best translation of a loop-free sequence by exploring all possible sequences that produce the same result. While there are several variants, in our case, we are going to be given a source program S and an objective function C, and we want to find a target program such that it is equivalent to the initial one and minimizes that objective function. And in order to do so, we are going to use a constraint solver for doing the search. So the problem with superoptimization is this very computational intensive technique, and this is because the search space is growing exponentially with the length of the sequences we are considering. So we have made 2 major contributions in this work. The first one is to propose a general superoptimization framework for handling this kind of stack-based bytecode. So we have applied it for WebAssembly, which I have already explained, but we have also applied it to the EVM. The EVM is the stack machine used for executing transactions in the Ethereum blockchain. And this is a very interesting case because in the EVM, it doesn't have any kind of registers, but instead, it uses some stack management operations. And it has also very interesting objective functions, such as the gas and the sizing bytes. This gas is a unit introduced by the Ethereum platform in order to measure the computational effort needed for executing a transaction and to charging the users accordingly. Our second contribution here is to introduce some novel components to improve the scalability of the algorithm, which are the 3 following ones. The first one is to improve the bound we are going to use in the search, and we are going to use here a greedy algorithm that constructs a sorted sequence. Then we have also developed a propositional logic encoding for doing a more efficient search than other superoptimization tools. And finally, we have introduced some domain-specific constraints to speed up the framework. So first, I'm going to introduce a bit the general stack bytecode language. So we have 4 different types of operations. The first one are the stack management operations, which are the ones that are operating directly over the stack. So we have pop, dup, that duplicates elements, and swaps, that swaps elements with the topmost one. Then we have some kind of memory operations. So here we are not assuming a concrete memory model, but instead we have some generic load and store operations. And the important thing here is that we annotate the different memory instructions we perform, so that later we have to consider the order in which they were in the initial sequence. Then we also have the register operations, which are the normal get and set, and we include also the T because this is very relevant for optimizing wasn't code. And finally, for the remaining operations, we have this 4th category, which are the uninterpreted functions, in which we are just interested in knowing for each operation how many stack elements are consumed and produced, and also whether it is commutative or non-commutative. Okay, so let's explain a bit the overall superoptimization framework. So how did we reach the previous example? So the first step was to extract the sequences from the program. And in this case, we built a control flow graph. We identified the different basic blocks, and we extracted jump-free sequences from them. For each of these sequences, we generated a symbolic state. This symbolic state consisted of the stack, registers, and memory instructions. For the stack, we determined how many elements were needed initially to execute the whole instructions. And for the registers, we just identify which ones are used in the corresponding sequence. We also compute some bounds using the symbolic state on the number of instructions, on the stack size we want to allow in the search of optimal solutions, and also on the number of registers we want to allow. The third step, which is a novel component, is use the greedy algorithm to construct, to produce a better bound. So in this case, we have reduced it from 13 instructions to 10 instructions. But also this greedy algorithm produces this code over here, which has 10 instructions and is better than the original one. Now we can do the search, and in order to do so, we are going to use a constraint solver. So we use the constraint solver and the previously introduced bounds, and this is the sequence we had considered before. Now, as we have set a time limit in the search, there are some situations in which we don't find any valid sequence. And in these cases, we can just choose the sequence from the greedy algorithm or the initial sequence. OK, so I'm going to explain a bit about the greedy algorithm. So the idea here is to provide a tighter upper bounds for the search. And the objective is to minimize the number of stack operations and register accesses that are needed. So the algorithm proceeds as follows. It starts with the initial symbolic state, and it is going to perform a series of functions that brings that state closer to the final one. And at each step, we are going to choose the best local decision. This means prioritizing actions that place the top of the stack in its corresponding position in the final state, or if I cannot do that, then I'm going to compute either a new stack element or a memory instruction. For this greedy algorithm, we have proven that it always terminates, and the produced sequence under certain assumptions is equivalent to the initial one. Now let's move on to the SAT encoding. So now we have this other sequence. This is extracted from the event, so it changes a bit. And we also have expressed how the stack evolves after applying each operation. So we start with a 0. When we do the push instruction, we introduce a symbolic variable S1, and so on. So the idea in our encoding is to fix the number of stack elements we want to allow in our search. And also, we want to fix the number of instructions we want to allow in the search. So as you see here, we are introducing those empty values to represent that the stack is shorter. For each of these positions, we would introduce some kind of variables that represent the contents of the stack after performing an arbitrary number of operations. And we're also going to introduce some variables to represent which operation is applied at each program point, so that by looking for the different combinations of these operations, we are going to explore the valid search space. But as this is a SAT encoding, we have to do some modifications. So consider the stack state at a given step I. And what we do is, for each of these positions, we introduce an array of Boolean variables that represent which stack element we are computing at a given step. This means that we have to add some additional constraints to enforce that only one of them is assigned to true at every step. Okay, the limitation, so we can follow this construction also to build both the registers and also the program sequences we are considering. However, this is not enough to specify the objective function we want to optimize. So our proposal here is to apply partial weighted MaxSAT techniques. So the key thing of using a MaxSAT solver is that it tries to minimize the sum of the soft constraints that are not satisfied. This means that we can represent different objective functions, such as the one I mentioned earlier, and also, in general, even more complex objective functions can be expressed using this framework. And we are also proposing a cheaper alternative that makes use of an incremental SAT solver in order to optimize the number of instructions in a valid sequence. Finally, here we have some domain-specific constraints that are going to be introduced and are used to speed up the search. Okay, so I'm going to conclude with some of the experiments we have performed. So we have performed an evaluation using different tools and settings. So we have compared our SuperStack tool with other systems, such as the Gasol superoptimizer for EVM and the WSuper superoptimizer for WebAssembly. We also have analyzed the greedy algorithm as a standalone configuration, and this is because we realized that it worked really well in practice. And finally, we have the superoptimization with and without the new constraints. Here, we have used 5 different benchmark sets, 2 for WASM and 3 for DVM. In the case of WASM, we have the benchmark set of the WSuper paper, and we have also downloaded some WASM programs from the library of Zircon. The Zircon language, well, is a language used for building arithmetic circuits in zero-knowledge protocols, and it's very popular, and that's why we chose it. Finally, for DVM, we have downloaded different types of data sets. So we have 30 smart contracts that were used to evaluate Gasol, 1,000 that were recently deployed, and some of the most recent but also most cold smart contracts. So here, I'm going to show you a bit of the experimental results. So we have the different benchmark sets, and for each of them, we both measure the results for our computing systems and for SuperStack. This is done in terms of the overall time and the percentage of gains compared to the initial code with respect to the corresponding criteria. Also, we have these 2 last columns that compare the speed up and also the boost, which are the percentage of additional gains that SuperStack is achieving. So for the first benchmark set, we can see that our superoptimization process manages to obtain extra 9% savings in instructions. For the second benchmark set, we don't have results for WSuper, and this is because WSuper must, for optimization through WSuper must go through the LLVM pipeline, and in the case of these WASM programs, they are compiled directly to WASM. But this one is very interesting because we can see a really high reduction. And this is because the Zircon library is not that well optimized, but also because our combination of different analyses allows us to achieve these great optimizations. Then for the EVM, the results are more or less similar for all benchmark sets. So first, I'm going to explain a bit about the greedy algorithm. So it is orders of magnitude faster than Gasol, but this was also clear. But also, we can see that it manages to obtain more gains than even the superoptimizer. And this is because the greedy algorithm can handle really large sequences. Also, we can see that the speedup is also very noticeable for the full superoptimization framework. And as you can see, well, it has a speedup of 4 to 6 times faster. And also, it manages to obtain twice or even 3 times as many savings as Gasol did. Finally, we can see that the domain-specific constraints we have managed to reduce the overall time in general by at least half, and even in the second case by 10 times, while keeping or even achieving more gains. So for future work, we realized that the greedy algorithm works really well as an optimization step on its own, and we're planning to implement it in the Solc compiler, which is the most used compiler for generating EVM code, and in particular inside the Joule intermediate representation. We also want to do more research on different strategies to improve the overall performance of the tools because we think there is a lot of room for improvement. And we want to extend the framework to support other languages, such as the Java virtual machine. So in the paper, you can find the complete formalization of the superoptimization framework. You can also find an explanation on the greedy algorithm, the SAT encoding, and the different domain-specific constraints we have introduced. So this is all. Thank you.
We have time for a few questions. Till people prepare to ask you questions, I have 2 of them.
OK.
So one alternative approach to super optimization is to take a stochastic approach.
Yes.
Like Stoke. Have you explored it, and what were the results?
No, we haven't tried it, but yeah, that's something we would also like to try to see if the super optimization approach would work with these stochastic methods. What we did try was using an incomplete MaxSAT solver that tries to do some stochastic search, but it didn't work better in practice. So that's why we have this approach over here.
Hi. Thanks for the nice talk. And I'm curious that in user optimization problem, and we use a greedy algorithm first, and then use a meta-heuristic algorithm such as genetic algorithms or simulated annealing layer for the more performance. So I'm curious, why didn't you use it only greedy algorithms?
So here, yeah. So what implementing heuristics inside the SAT solver is very difficult. So if we rely on the search in the SAT solver, then we rely on the heuristics that are already implemented in the tools.
However, in this research, grid algorithms are used in the making a tighter bound, right?
Yes.
So meta-heuristic algorithm usage for just making a tighter bound can be useful because it is completely orthogonal with SAT solver.
Can you repeat, sorry?
Sorry. I think it is orthogonal with SAT solver because in this research, grid algorithms are used to make a tighter bounds of the search space. So
yes.
Isn't it?
Yes. Sorry? Well, I can later.
Maybe take this question offline.
Yeah.
Okay.
So any other questions? Let's thank the speaker.